see where they came in from.
Yeah. So we're now broadcasting, so that's
okay.
Cool. Right. Talk to you later. Right. Good morning, everybody. My name is Nigel Hedges. I'm here together with Rob Jewell, my colleague from Fluke Networks, to talk to you about new developments in our OTDR environment, specifically the high dynamic range OTDR, which is intended for targeted single mode applications, which we'll come to in a minute or two. I will switch off my ugly mug at the moment so that you don't have to watch that all the way through. And let's see where we get to. Now, I hope, accept my apologies, some of these slides are close relations to some that I showed a couple of weeks ago. Hopefully I won't bore you to death. So, OTDRs, optical time domain reflectometers, the primary troubleshooting tool for fiber installations of all types, optical fiber, used in everything from telecoms to aerospace and automotive and pretty much everything in between. Loads of different fiber core sizes, loads of different connectors involved. There are specific environments where, particularly in the single mode environment, where issues arise which require particular sets of capability. So let's step forward swiftly and look at a simple explanation of an optical time domain reflectometer. Sorry, just a sec. An optical time reflectometer, we try and simplify that, and we say an OTDR uses pulsed modulated light at specific wavelengths, those are the same wavelengths at which data is transmitted, to measure fiber length and distance to event, or whatever happens on the fiber, whatever impacts the performance of the fiber is measured in terms of distance away. OTDRs will also indicate power loss at each event, and most modern OTDRs today will give you an overall loss end to end, because that's what determines whether or not a signal transmitted from one end will arrive at the other. Most OTDRs will also indicate reflectance loss. And you'll notice I used the word measure when we were talking about length, and I used the word indicate about power loss and reflectance. And the reason for that is that OTDR does not have a true meter function. It doesn't have a calibrated output necessarily, and therefore indications of power loss and indications of reflectance tend to be less accurate than if you had used a light source and power meter to produce them. Typically, we expect to see somewhat less loss indicated with an OTDR than with light source and power meter. OTDRs are not all equal. OTDRs are built for different jobs. Some of them are for long-range telecoms work, and therefore they have huge power supplies, huge amounts of power that's fired into the fiber under test. They need to have the ability to transmit a pulse of light over several thousand kilometers. The net result is that while they're very good at testing over several thousand kilometers, their typical resolution is then in terms of kilometers or hundreds of meters. Well, that's appropriate for telecoms, but it doesn't really work in an enterprise environment or a campus environment, or the type of places where the fiber links are measured in terms of kilometers, not in thousands of kilometers. Some units are short-range, high-resolution units, and that's really how I would characterize ours. The Fluke Networks OTDR portfolio comprises essentially two main units. The standard OTDR, which we use in data centers and typical campus installations, and this new one, the high dynamic range variant, which is specifically for single mode applications. Another thing typically that we see is that modern OTDRs use sophisticated software to make it easier to understand what's going on. A huge number of people will look at the OTDR trace that you see on the right. They see the heartbeat pattern, they nod wisely, and they have very little idea what is going on that trace. So one of the things we have the ability to do is to convert that trace into a picture. We call it an event map. That's a marketing term, but essentially it is a diagram of what's happened from the OTDR down the length of the fiber, with length measurements, with indications of where the connectors exist, where the fiber ends, and those kind of things, and make it much easier to understand what is going on. And then all OTDRs have limitations. All OTDRs have event and measurement dead zones, which vary depending on their design and their intended use. An event dead zone is the distance behind one event or one happening along the fiber, during which the OTDR is unable to detect another event. So you could call it a shadow behind the event, and depending on the design of the OTDR, that can be a very short distance or a very short period of time, or it can sometimes be quite a long. A measurement dead zone is different in that is the distance behind the first event before the OTDR can measure the performance of the next event or an additional event. So event dead zones are how far before we can see a second event. Measurement dead zone, how far before we can measure an additional event. Dynamic range is always a question, and it used to be always the first question that operators would ask: how much is the dynamic range? The argument being that the more dynamic range you have, the better off you are, is not entirely true. Dynamic range should be appropriate to the intended use. You do not have to have masses of dynamic range in a short, let's say under 200 kilometers, in a short link which has relatively few bends connectors in it. It's just a waste, and you end up with an awful lot of ghosting going on. So dynamic range needs to be appropriate, and OTDRs typically work best when launch and receive fibers are used. That's because obviously the OTDR is operating at the speed of light, and a pulse of light has a known period. So it might be a microsecond for the sake of argument. that's quite a long pulse. A microsecond pulse has a length associated with it because of the speed of light. So when we turn the light on, microsecond later we turn the light off. Where is the front edge of the light? Well, it's a significant distance away. So launch and tail fibers make a huge difference to being able to see the performance of connections. We cannot measure the performance of a connector on its own. We can only measure the performance of a connection. That is true of all OTDRs. That means that if you want to measure the performance of the far end connector, you need to have a tail fiber plugged in or a receive fiber plugged in so that the light has somewhere to go and you can measure the performance of the complete connection. And possibly most importantly, all end faces need to be clean prior to testing. And I apologize if this is something that you hear on a very regular basis, but we still see an awful lot of people using OTDRs and getting questionable results, and the questions relate to the condition of the connectors that they are plugging into. So we need to bear that in mind. So having simplified the OTDR to that point, let me show you our current range. All of these units, I'm sure you're aware, use the same mainframe. So this is the new module. The high dynamic range module is a plug-in for the existing Versiv platform. If you have a Versiv model of any description, the high dynamic range OTDR will plug into it. It is the only one with the pretty green cap that you see here. So this is the HDR OTDR, but obviously we have units for other environments as well. And the important thing here being that the HDR high dynamic range unit only operates in single mode, so it only ever has one port on the top, well, one port plus the visible light source, and always operates at 1310 and 1550 nanometers, and then there are optional 1490 or 1625 nanometer outputs as well. And you can opt to have just the two or either of the three, 1490 or 1625 outputs at the same time. So why the HDR module? Well, attaches to the Versiv mainframe, as I said. We had originally intended it for datacom installers, outside plant contractors. More recently, we've also found a number of end users who had specific requirements for testing of single mode fiber, particularly in the metropolitan rail area environment. They require high dynamic range for links, including passive optical networking splitters, which are particularly demanding when it comes to testing of last mile, and for addressing data center applications which require higher dynamic range, like ultra low loss single mode fiber, where we are specifically seeking information about macro and micro bends, which may or could impact the performance of the fiber. So we have applications to include utilities, campus, access, perimeter security, identification and location of macro bends, which are the primary culprits of loss in single mode environments, fiber to the X, or fiber to the home, the building, the apartment, etc. And last but not least, enterprise wide area networks, last miles, multi-unit dwellings, and passive open networking over local area networks, otherwise known as POL. All of these have requirements for additional dynamic range. We build our additional dynamic range into the module, but we have not seen fit to extend the unit's maximum distance beyond the 130 kilometer range. So we are still in the short range, high resolution environment here, and we are looking very much to the last mile and to data center applications with this particular module. I plan, in fact, to show you the module connected to my mainframe during the course of this presentation. So we'll move on from there. Obviously, as I started out saying before we do anything else, we need to think in terms of inspection and cleaning of fibers. Again, this is something that I'll show you, but I have to show you the classic transfer of dirt. This is a nice clean fiber end face, and this is one which I wiped on my shirt, which isn't quite as clean. If I plug the clean end face and the dirty end face together, the fact that the two are physical contact connectors will result in this, which is an end face which is contaminated. But as you can see, due to the geometry of the end faces, the contamination is forced into this circular pattern on the fiber end face. Now, typically what will happen with that is that over time, the contamination will migrate across the end face, and you will see a reduction in performance. We definitely don't want that, and certainly neither of those two dirty end faces would approach passing the condition standard, which we all know and love, or not. So what's absolutely essential there is that we clean the launch fibers before every mating. We think about making sure that everything is clean, not only our launch fibers, but also the fibers on the installation themselves need to be in excellent condition before we plug the OTDR in. There is no point in plugging the OTDR in to a dirty port. You will only get poor results. So OTDRs have a significant role in troubleshooting, and obviously if you don't have an OTDR available, then the best you can do is to shine a bright light down the fiber, try to determine whether it comes out at the far end, but not at any of the connectors. Any kind of a glowing connector is a sign of an issue. You can inspect and clean the end faces, and you can replace the link or re-terminate. The joy of this is it's a small investment, you're very limited in diagnostics, and you are limited to trial and error when it comes to getting test results out. With an OTDR and clean end faces, obviously we can get really nice indications of where the issue is or where the issue appears to be, bearing in mind that we always want to test in both directions. So we're testing upstream and downstream, and we may find that an issue which appears to exist in one direction does not exist in the other. That is usually an indication of a small change, or in some cases a significant change, in the index of refraction, as we go from the launch fiber to the fiber under test. In these images, what you're looking at is the OTDR at the bottom of the screen here. Then the launch fiber is always colored gray. The installation is always colored black. Good connectors are blue, bad connectors are red. And the tail fiber is once again colored gray. So we have a really good indication of where the issue exists in one direction and possibly not in the other. So let's move on from troubleshooting and look at certification or testing for performance. And certainly in the data environment, and I have to split the story here between testing in a passive optical network environment and testing in a data center or enterprise environment. Passive optical network environment, typically we are testing a single fiber. In a data center environment, typically the fibers are deployed in pairs. So we tend to test them in pairs because one is transmit and one is receive. For certification of those fibers, we have two test regimes. One is called the basic test regime, the other is called the extended test regime. And irrespective whether we're a US allied company, in which case we look at TIA 568 as our reference standard, or an ISO organization, in which case we look at ISO 14763-3, there are two test regimes, and the basic test regime is the light source and power meter, which we see over here, which we see here. And that is excellent at measuring loss and is the most accurate measurement of loss, but gives us absolutely no indication about where in the fiber the loss exists. The OTDR is the one which is responsible for telling us where the loss happens, and we are, in terms of both standards, we are required always to do the light source and power meter, and we can opt to add the OTDR test result. In standards terms, it is not possible, or it's not allowed, to use the OTDR alone to certify fiber. And certainly none of the manufacturers who offer warranties on their fiber solutions, as far as I'm aware, none of the manufacturers will accept OTDR test results for warranty purposes. Light source and power meter is required for warranty. But if your client wants to know where in the installation he should go to improve the loss of the installed fiber, then the OTDR is the one which will indicate where the loss is. And obviously will also identify bottlenecks. Now, we make this easy in a data center environment by testing with a smart loop. The smart loop concept means that we test a transmit and receive pair at the same time by using a smart loop at the far end. The great joy of this is that it forces the operator to perform the OTDR tests correctly, by which I mean it requires him to test both fibers in both directions at the same time and produce a bidirectional average. It also means that by definition, you must use a launch fiber, a smart loop fiber, and a tail fiber, and it avoids any adaptation with hybrid cords, and it ensures that we handle the launch and tail fibers correctly, which fundamentally means we leave them in place. At the same time, it also reduces testing time by something over 50%. And with a bit of luck, the poor old technician is not on his own, although if he is, then 2 or 3 smart loops mean he can test multiple pairs before he has to run down to the far end to move the loops around. And the smart loop looks like this, and I'll show you this later on. So the first phase of testing is that we test down what is determined as fiber A here, so let's call it the transmit fiber, through the launch fiber into fiber A, to the far end where there is a smart loop, which is another launch fiber, which directs the light back down fiber B, which is the RX fiber from the near end, to the tail fiber, and we get one measurement in that direction. Then we disconnect from that launch fiber, we connect to what was the tail fiber, and we test the other way round. So through the RX fiber, through the spare launch fiber, into the TX fiber, and back into what is now the tail. And the net result is that we get 2 fibers tested in 2 directions in a relatively short space of time, and automatically we're able to calculate, or the OTDR is able to calculate, the bidirectional average, which is the valid test result for each of these 2 fibers. So you get 2 test results very swiftly. So bidirectional averaging is very much enables us to look at this, and yes, we have one connection which appears to have an issue associated with it when we test it in this direction. Then we test it in the other direction, and we find that that is now no longer an issue, but this connection has developed or is developing an issue due to directional issues. And when we average the 2 together, we find that what was a fail becomes a nice, clean pass. So directional issues related to index of refraction are dealt with by the bidirectional average. And the bidirectional average is in data center environments is truly the only standards-based, recognizable, acceptable test result. Every now and then we do come across customers who suggest that they would like to have an OTDR test in one direction. And frankly, there is very little value in an OTDR test in one direction, particularly if it isn't a clean pass. So this is obviously data center. This applies to single mode in the data center just as it does in to multi-mode. So bidirectional averaging is something that we do. Testing with a smart loop is something that we do. It reduces the length of time we spend testing and gives us valid test results almost without question. Right. So there we go. So at this point, I'm going to switch over and show you the live screen from my OptiFiber Pro, which is fitted with the green HDR OTDR module. We will have a quick look at end-face inspection, because one of the things which is true of the vast majority of HDR OTDR environments is that, and particularly where splitters are concerned, is that it uses APC, angled polished connectors, and they are a little different when it comes to inspection. And then we'll look at launch and receive fibers. We'll look at the splitter environment. We'll look at fault location and identification. And then we'll look at load loss single mode testing with a smart loop. And hopefully I can do all of that in a relatively short space of time. Let me just do that. And that. So I will bring across this. So this is the display from my Versiv mainframe. I have it currently set in fiber inspector mode, and what you're looking at the moment is an APC connector, and it looks a little shadowy because APC connectors are directionally sensitive. So we need to rotate the APC connector until we get the clearest possible picture we can, and then adjust the focus. And as you can see, this APC connector is not perfect. However, if I hold the camera still and rotate the APC connector, you'll see that it tends to disappear. And this is down to the fact that we need to get the angle right in order to be able to view the image properly. So that needs cleaning. I'm definitely not happy with that. So I'll give that a swipe with the cleaner so that we can use it later on. There, that's much better, much prettier. I've got another one to play with here as well, so I'll do that one as well. There is a slot in the camera adapter for APC, and it has an angle on it, so you can't use it for anything else, which helps to get the alignment correct. There we go. Just make sure. Okay, that one seems to have a mark on it. How tiresome. Okay, so that is a mark which is not cleaning off. That is not a good thing. Put the couch back on that, just gently, so that we don't lose anything. That'll be ready for later. Right, first thing we're going to do is we are going to go home, and here I have my project. It's all set up, and once again we have the auto mode. Now sophisticated OTDRs these days have an auto mode which adjusts everything to suit the installation under test. Old-fashioned OTDRs, previous model OTDRs, the auto mode was really only good for determining how long the fiber was. But these days, with significant amounts of development in software and artificial intelligence, the OTDR is much more able to determine what is happening down the length of the fiber using multiple different pulse widths, using multiple different filters. We can get an awful lot better picture of what's happening on here. So the only thing that I need to do is I need to check my launch fiber compensation before I start. So I go here, I go to set launch compensation, and down at the bottom here you can see that the current settings are 158.8 meters for the launch, 157.2 for the tail, and that was set this morning at 9:15. So I'm going to leave those as they are rather than resetting them, and I'm going to go home again, and I'm going to press the test button. Now, one thing which is certainly true about testing in a passive optical network environment is that we have an item. You'll notice that my port connection quality is excellent. That means that the connector between the OTDR and the launch fiber is really, really good and clean. And here we're starting to see the beginnings of a trace appearing on the screen. Different wavelengths happening at the moment. This OTDR is running 3 different wavelengths, the default wavelengths being 1310, 1550, and 1625. And losses should be greatest on the 1310. The 1550 and 1625 wavelengths should pretty much mirror exactly what's going on. So here we have our test result, and you'll see that the OTDR has identified a loss at 1244 meters from the start of the installation. So we start measuring length at this point. That's where 0 meters is, and the loss event is at 1244 meters, and it is a loss. You'll notice the black triangle in the corner of the red box. That enables us to identify that loss as either a loss or an APC connector. If we know there's an APC connector there, we can identify it as such on the test result. It won't change the pass to the fail to a pass, but it would help to identify the connector if we knew it was there. So if I change it to APC connector, then as you can see, that event is now a connector. It still has excessive loss associated with it, but it is there. Possibly, I'm going to change it back again. Possibly more importantly, we've also identified the presence of a 16-way splitter. This is an automatic detection, but here it is. So this is a 1/16 splitter. Now, bearing in mind, we are identifying which end we're shooting from, which is obviously the subscriber end. You can only really shoot a splitter in one direction because the loss going from the single end of the splitter to the multiple end is horrendous, and it also presents the OTDR with, in this case, 16 different ports to follow. So you only ever shoot splitters from what is called the subscriber end. In this case, this is a 16-way splitter, and we have it identified. We have its distance away identified, and we can see pretty much everything else going on. We also have a poor connection at the far end, just before the tail. Once again, the loss at that far end connector is higher than we would like it to be. So we have the ability, without pretty much setting the OTDR up at all, to produce a test result which is entirely valid, which shows everything that is happening down the length of this fiber, indicates where the splitter is, which is possibly the most important piece of data as far as most installers are concerned. And it gives us a very nice picture. We also have the trace, and bear in mind in this case, because we can only shoot the splitter upstream, the trace will only be valid in one direction. You can see the start and end of the fiber. Start is indicated by the dotted line, the end by the beacon, because that's where I left the beacon on the event map. If we wanted to see where this loss is on the length of the fiber, I can change it so that the beacon now appears on the trace at the loss point. That waterfall display to the left of it is obviously the splitter. That's the massive loss generated by the splitter. But as you can see, the three different wavelength traces all follow one another really nice and closely. So that tells us that we are getting a true representation of this fiber installation. And those of you who are wondering how I happen to have 2.5 kilometers of fiber in my study, I'm just lucky, and we have a demo box that has that much fiber in it. Now, this is great. Obviously, fully automated means we don't have necessarily a huge requirement for training. We can adjust setups if we want to, but equally, I'm going to exit from that. And I'm going to say that's auto passive optical networking, but we can also have a manual passive optical networking setup, which is here. And manual passive optical networking works in a slightly different environment, or in a slightly different way, because we can set up all sorts of settings that otherwise would be automatic. So we can do things like identify splitters. So we can identify what type of splitter we might have. We might say, okay, what is there here? And we can actually go discover. We won't want to save that as a test result, but we can go and discover splitters that we know exist. And the OTDR has enough inbuilt intelligence to be able to come back to us and say, I see a splitter, and this splitter has all of the characteristics of, takes a little while, but you obviously only need to do it once for each type of splitter. Splitters have relatively specific characteristics. So when you get, when the OTDR identifies the presence of a splitter, it can usually also identify what type of splitter it was. I should have asked it to look for 1/16. I forgot. My apologies. So we can set up for splitters. My apologies, I forgot to do that. We can select the range that we're going to look at. So in this case, I have 4 kilometers of fiber less than. I can set the pulse widths. So for instance, I can choose, in this case, to select a specific pulse width or not. I can choose the averaging time. We choose 10 seconds because we've got 3 things. Ends, thresholds, loss thresholds. You know, we can set the loss threshold at 0.5 dBs. and we can set up the macro bends. So macro bends are detected by the difference in loss between two different wavelengths. So we can set up the macro bend thresholds here if we want to. I'll leave them as they are, and then I can hit done, and I can run a test using the manual testing just like that. The only thing that doesn't happen with manual passive optical networking is we don't necessarily get automatic detection of the splitter or identification of the splitter. So this will take 35 seconds, during which I won't sing you a song because I'm a terrible singer, but with a bit of luck, I will be able to produce a test result at the end of it, which will be fascinating. Passive optical networking, really a different environment for most of us. Not enormously scary as long as we recognize that the splitters themselves have very typical performance behaviors. Let me go back to the event map because we will still have stuff on the event map. So here is the event map. We identified, in this case, a 16-way splitter. And here we need to tell the Otdr that that is an APC connector. It's still a bad APC connector because it's the same one that we had under auto. But in this case, the Otdr recognizes it as an event, but we need to tell it that it is the connector at the far end. Also notice that launch compensation is not used by default in manual Otdr mode. So you can see that the launch fibers are there, but they are no longer identified specifically as launch fibers. I could switch that on and then they would be identified as launch fibers again. And the Otdr would look at that 158 meters at the far end and would recognize it as the far end tail fiber, and would then probably recognize that connector as being a connector rather than a loss event. So here we are producing test results which are valid in the splitter environment, given that in a splitter environment we can only test from the subscriber end. Otdrs are not able to test the other direction in the vast majority of cases, and will produce extremely confusing results if your 16-way splitter is terminated to 16 fibers. Your test result looks horrendous from the far end. So you only get valid Otdr results in a splitter environment when you are going upstream. Let me show you a slightly different thing now. So I need to go home. I'm not saving any of this data. I'm going to go back to the auto passive optical network Otdr. And I'm going to use selected, and I'm going to show you a different fiber. This one is kind of nice. Doesn't have a splitter in it, but it does demonstrate a particular function. Let's see how this one goes. So here we have no splitter, and what you'll see with a bit of luck is that because there is no splitter detected, the test time is significantly reduced. That's because when the Otdr detects a splitter, it then has to test the splitter with multiple different pulse widths and wavelengths in order to confirm that it is the type of splitter it thinks it is. If it's going to report it as a 16-way splitter, it needs to be certain that it meets those criteria. In this particular case, this is a different type of issue. We have a bend detected 0 meters from the far end of the fiber. So we now have our launch and tail fibers back. First connector, which is this one here, is at the launch point, has a small associated loss. There is no problem associated with it. In the middle of the fiber, there is a 1 dB loss at 250.75 meters. And we could say that's an APC connector, but it isn't. It's a loss. But most importantly, we have this bend. And the bend is at the far end of the installation, essentially at the far end connector. And this is what happens in single mode environments when the installation is forced into a particular configuration, and the net result is that you get a very tight bend immediately behind the connector. And that very tight bend contributes significantly to loss. So we have a bend detector built into the unit. It looks for, as we saw before, those differences in loss across the trace. And here you can see those differences in loss across the trace. This one here will be 1310, 1550, 1625. I have 3 different traces running, and that is what determines that the unit has identified a significant bend. I suppose we could call it a debilitating bend in the fiber installed here. So we have the ability to identify splitters, to position them correctly along the length of the fiber as long as we're testing upstream. We also have the ability to look down the fiber and to determine whether there are debilitating bends or performance reducing bends in the fiber, and also where they are. In this particular case, it's right at the end of the installation, which is where we often see them in high performance single mode installations. They tend to be sensitive to how they are plugged in at the patch panel end. So the last thing that I wanted to show you this morning was the smart loop test, because that's useful in single mode environment. So I'm going to go home with the tester. I'm at home, but I'm going to press the home button, and I'm going to change the test setup to smart loop OTDR, which is here, and use selected. And this is bidirectional. I've selected only 2 wavelengths, 1310 and 1550 for this. We are going to be testing 2 fibers. We're going to be testing 2 fibers, 1 upstream and 1 downstream, and then we're going to reverse the chords. And I need to check that I have valid launch compensation. So here we have smart loop is set up. I have launch and tail. Should have smart loop as well. I think possibly I better do that again. This one, and then 2. So I'm connecting my 3 launch fibers together. 1 launch, 1 tail, 1 smart loop. And I press the set button. And I don't want to save that test result today. And I still have a good clean port, which is nice to know. And so there we have 3 launch fibers, one of them from the OTDR port to the launch point, 160 meters, another one to the tail, which is 155.89, and then another one to the end of the fiber, which is 314.01, and we hit save. And we say OK, and we go home. And now we're ready to connect to the link under test and actually test the pair of fibers. So I'm collecting my launch fiber to one end of the installation, I'm connecting my smart loop to the far end. In there. You'll be pleased to know that I did clean and inspect all of these fibers this morning because, you know, I'm very picky about that. And the tail fiber goes in at the near end again. There we go. Make sure they're all plugged in all the way because that always helps. Press the big yellow test button. And again, with a bit of luck, because we're not in a splitter environment, we should get nice short test time. And then we will receive an instruction to reverse the test calls, or rather to disconnect the launch fiber, which now becomes the tail, and connect the tail fiber to the top of the OTDR, which now becomes the launch. You'll notice that there is in the picture, there is a small sacrificial cord in there. That is the port saver. That is there to protect the port so that we're not constantly plugging and unplugging potentially dirty cords directly into the optics of the OTDR. So I've reversed the cords, I can hit done, and the unit will go away. And in another 13 seconds or so, with a bit of luck, yeah, 13 seconds will provide us with a second test result for these two fibers. So, nothing ever, some things don't always work according to plan. In this case, the return fiber test was not able to detect the presence or both ends of the loopback fiber, and the net result is that we get a slightly different result. So what we have at the moment here is we have fiber A end 1, okay, fiber A end 2, but we don't get a bidirectional average, which is extremely irritating because it was working beautifully this morning. Now at this point, if we were in the field, we would clean the end faces of the smart loop fiber, which is something that I can do, and we would try again. However, that would require an additional 40 seconds or so, and I don't think we're going to add an awful lot from this. Please just accept that bidirectional average is the valid test result. And the net result here is that we have a fail in our test result, primarily because we couldn't see the connectors of the loopback fiber. So I'm going to now close that down and go back to my PowerPoint slides, because there are a couple of things that are worth talking about. After OTDR testing, it is always worth using the camera to get end face images, because they form part of your test report. They are part of your defense in the event of the fiber not working after 6 months or so. And that is usually, or sometimes, down to the work practices of the client. They do not always clean the end faces before they plug stuff in, and the net result is that you end up with end faces which are either dirty or damaged or both. But if you have end face images from when you left site, so at the end of testing, if you have end face images when you left site, then you have decent defense that it is not your fault that the fiber isn't working. If you are particularly specific, then you would use the industry standard, which is IEC 61300-3-35 edition 2 at the moment, which specifies how much dirt you can have in each zone of the fiber end face, how much dirt, how much zone, how much damage, and will give you a really good indication of whether or not the fiber can be expected to perform. Then obviously we upload our test results in most instances. These days a lot of people are using our Linkware Live cloud service, which works beautifully. The latest version of the Versiv mainframe has inbuilt Wi-Fi, so you don't even need a Wi-Fi dongle anymore. If you don't have Wi-Fi available, then there is an RJ45 port on the bottom left corner of the tester, which would enable you to plug it into a wired network. As long as the wired network has access to the internet and you can authenticate the unit on the wired network, your test results will be in the cloud in about 30 seconds. And obviously from there we can produce the test reports that we know and love. That one's a copper one, this is a fiber one. This is a very comprehensive fiber test report, so it has light source and power meter test results. It has OTDR test results with the bidirectional average, and also the directional tests, N1 and N2. This is for a single fiber. And the event map is all included in the test report. More importantly, perhaps, also included are the end face images. Now, the end face images are time-stamped, so they should indicate that the end face images are those taken as you leave site, not as you arrive on site. So the client should be able to very clearly understand that when you finished the testing and covered the installation up, the end faces were clean and undamaged. That's the important thing. Right, ladies and gentlemen, I thank you for your attention. I'm very happy to take questions. I'm sorry, I forgot to say at the beginning of the thing, if you have questions, you can bang them on the question bar. Rob is monitoring the questions and is also monitoring the chat, hopefully. So if there are any questions, I'll do my best to give you clear answers.
We're all clear at the moment, Nige.
Oh, excellent. 13 people with no questions. Either I was really good or everybody's gone to sleep. Either one of those is possible. Well, I can switch my video back on so that you can see how desperate I am to answer a question. Yeah, I'll do my best with whatever you ask. Otherwise, thank you all for attending. Rob, thanks for looking after all the back office stuff while I was rabbiting away. Anything I need to add? If there are no questions, I will shut this down and end the meeting. Is everybody happy with that? Thank you very much indeed. Take care. Have a great day. Look forward to talking to you all soon. All the best. Bye-bye.